ഗുഡ് മോർണിംഗ്. അപ്പം ഇന്ന് നമ്മൾ സൈക്കിൾ കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ സൈക്കിൾ ട്രാൻസ്പോസിഷനൊക്കെ കുറിച്ച് പറഞ്ഞു. പെർമ്യൂട്ടേഷൻ ട്രാൻസ്പോസിഷൻ്റെ പ്രോഡക്റ്റായിട്ട് സൈക്കിൾ ട്രാൻസ്പോസിഷൻ്റെ പ്രോഡക്റ്റായിട്ട് എഴുതാൻ പറ്റും. അതുകൊണ്ട് തന്നെ പെർമ്യൂട്ടേഷനും പ്രോഡക്റ്റ് ഓഫ് ട്രാൻസ്പോസിഷനായിട്ട് എഴുതാൻ പറ്റും എന്നൊക്കെയാണ് നമ്മൾ കഴിഞ്ഞ ക്ലാസ്സിൽ ഡിസ്കസ് ചെയ്തത് അല്ലേ. അപ്പോൾ അതോടുകൂടി ആ സെക്ഷൻ അവിടെ തീർന്നിട്ടുണ്ടായിരുന്നു. Now we'll move on to next section, that is section 10 in this module. That is the last module in this, last section in the second module. Okay, this is the last section in the second module. So we'll, in this module, section will understand a very important theorem, the theorem of Lagrange. Which will give you an idea about the order of a group and the order of its subgroup. Okay, is there any relation connecting between the order of a group and the order of its subgroup? Okay, and the theorem says that the order of a subgroup always divides the order of the group G. Okay, now for this the intuition behind the theorem is that if G is a group, okay, if G is a group and if you partition G using an equivalence relation into different cells, say R cells, okay, then for any subgroup H of G, will show that R into order of H is equal to order of G. So this is the the outline. This is the way used to prove Lagrange's theorem. So number of cells is R. So R into the cardinality of H, that is the order of H, is equal to order of G. This is the case. So here we need this cell, right? That is, we need an equivalent relation that partition the given group. Okay, so we'll define a new equivalent relation in this section, that is known as cosets, and we'll see what do you mean by a coset. Okay, now we'll begin this section with a theorem 10.1. The statement of the theorem is that let H be a subgroup of G and let the relation equivalent L be defined on G by A is equivalent to B with respect to L if and only if A inverse B belongs to H, and let equivalent relation R be defined by A is equivalent to B with respect to R if and only if AB inverse belongs to G. So L stands for the left on the inverse, R stands for right on the inverse. Okay, so then we'll prove that these relations are both equivalent relations. Okay, so we'll prove it. First we prove that the equivalent relation with respect to L is an equivalence relation. The relation is the equivalent relation, and in the similar way we can prove that the equivalent R is also an equivalent relation. Okay, so H is a subgroup, and we know that H satisfies all the axioms of subgroup axioms, that is, it is closed under the operation, identity element exists, inverse also exists. Now to prove the reflexivity of this relation, let A belongs to G. Then we can see that A inverse A is nothing but it is Z, and E is definitely in H because H is a subgroup. So what we got is A inverse A belongs to H for all A belongs to G. That means A is equivalent to A under L, right? Now for the symmetric property of this relation, suppose A is equivalent to B under L, then by definition A inverse B belongs to H, right? Now we know that H is a subgroup, so existence of inverse is there. So whenever A inverse of B is in H, its inverse is also in H. So inverse of A inverse of B is nothing but what? B inverse into A inverse of inverse, that is B inverse into A. So B inverse of A belongs to H we got, right? Now B inverse of A belongs to H means B is equivalent to A under L, right? Now to prove the transitivity of this relation, suppose A is equivalent to B and B is equivalent to C, then by definition A inverse of B in H and B inverse of C in H. Now two elements are in H, and we know that H is a subgroup, so it is closed under operation, so the product of these two elements are also in H. So A inverse of B into B inverse of C is also in H. But A inverse of B into B inverse of C is nothing but A inverse of A inverse of B inverse C, that is A inverse of C, right? So A inverse of C is in H implies A is equivalent to C. Thus, our relation is a equivalence relation. So we can definitely define a partition of G. Okay, now the question is what are the cells with respect to, or what are the equivalent classes with respect to this equivalence relation. So let us find the cells in this partition. Suppose A belongs to G. We need to find out the equivalent class containing A, or the cell containing A. So by the definition, the cell containing A is what? It consisting of all x in G such that A is equivalent to x under L, right? So A is equivalent to x means what? All x in G such that A inverse of x belongs to H. So A inverse of x in H if and only if what? A inverse of x equal to some small h for some h belongs to H. So what we got is that x belongs to AH for some h belongs to capital H. So the cell or the equivalent class containing A is nothing but it is the set of all AH such that H belongs to capital H, and we denote it as small a h, A into small h, capital H. Okay, so in similar way we can show that equivalent relation with respect to R is in also an equivalent relation, and the cell containing A is nothing but it is capital HA. Okay, so since G is not an abelian group, H and HR may not be equal. Okay, so this subset of group of a given subgroup H of G is known as left and right coset. The first one is left coset and the second one is right coset. So these cosets are obtained as the partition of what? A partition of the given group G with respect to these two relations. Okay, now let us discuss two examples to find out the cosets of the given subgroup. First question is find the left and right cosets of subgroup 3Z of EZ. So 3Z, definitely 3Z is a subgroup of EZ, and using the additive notation the cosets of 3Z's with respect to EZ are nothing but it is M plus 3Z where M belongs to EZ. So I am taking values for M is 0, 1, 2, etc. And when I take M equal to 0, I got 3Z plus 0 is 3Z itself, same set. M equal to 1 implies 1 plus 3Z. So I'll add 1 to each element of 3Z. So adding means the usual addition here. Okay. So I'll get the coset as 1 plus 3Z is equal to what? The set containing 1, 2, 1, 4, 7, etc. And in the left it is minus 2, minus 5, minus 8, etc. Similarly, M equal to 2, I'll get 2 plus 3Z. And I have stopped finding the coset because you can see that union of these three collections, these three cosets will give you what? Z itself. So this is the these are the partitions, right? So we need only partitions. So these are the what? These are the cosets that constitute what partition of Z. We are only interested in the partition of that Z. Okay, those concepts which constitute what partition of the Z. So because the next will be same as M equal to 0. That is the case we are getting. Okay. So these are the only cosets of Z which constitute the partition of Z. Understood? Next is the cosets of 0, 3 in Z6. So I can find cosets of other subgroup in the similar way. So you have to do yourself. This one I have done for you. 0, 3 is the subgroup. Definitely it is a subgroup of Z6. So I am here also I am using the additive notation. You can check the multiplication notation also. So I am giving, we can see that A plus 0, 3 is the what? The cosets, right? So I am putting A equal to 0, 1, 2, 3. So here not that A equal to 0 means same set I am getting. A equal to 1 means you have to add 1 to each element of this subgroup 0, 3. And adding means addition modulo 6. Okay. I have simply written here 1 plus 0. It is nothing but what? 1 plus 0, 6 modulo. Okay. I haven't written that one, but that is, you should understand. That is our binary operation on Z6. Understood? So beware of that one. So A 1, 2, 3. After getting 3, again I am getting the same subgroup 3, 0. So I can stop. So what are the different cosets that constitute subpartition of Z6? It's for A equal to 0, 1, 2, right? So 0, 3, set to 0, 3, set to 1, 4 and set to 2, 5 are the cosets which constitute partition of Z6. Okay. So these are the today's class. I hope you understand the concept. Now, uh, once again, I would like to tell you that you should read textbook also very, very well, because all the things in the textbooks are not mentioned here. So you should follow textbook at the same time. Thank you so much.